All right, good evening. So here we are. We have to push on to 3.1, but I will put up some other things for you guys. All right, this is probably, chapter 3 is probably going to be the hardest one you've encountered so far because it's a little different. It starts off kind of easy. We're going to have plenty of time for you to actually get bored of doing the problems, which is always a good thing. I'd love to hear you all say, "Oh, these are so easy and so boring. I can't do another one." Okay. But here we are. The beginning of this is not going to feel that way. It's going to be a rough journey. So we have something called a one-to-one function. We're going to start covering something called inverses. And in order to have an inverse, okay, inverse in math, we're just going to mean it undoes it. Okay, a function that has something undone. So the idea is like, well, if I've got a square root of something, right, how do I get rid of it? And the idea is you square it. So you'll have x is equal to 9. So in this case, right, in this case, the square root and the square function are inverses of each other. They undo each other. Okay, same with cubes and cube roots. Okay, so here's the first idea: is a function must be 1-to-1. That looks like this. Okay, to have an inverse. Okay, what this also, the way to test whether this is true is, does the function pass the horizontal line test? All right, and that, so if I've got, say, the square root, right, that's what the square root function looks like. Right? Can I pass a horizontal line through this function and only hit the function once? Yep, only hit once. Passes the horizontal line test. But you might say, wait a minute. If square roots and squares undo each other, right here is y is equal to x squared. This does not pass the horizontal line test. Like, you're right, it doesn't. So what we have to do is we have to make that happen. So we have to choose, right? We have to choose the domain. So if we say, well, that's true for x is greater than or equal to 0, then we only get this part. And now it does pass the horizontal line test. Okay, so you are allowed to manipulate the domain so that a function has an inverse, but maybe only in a particular spot. All right, you're going to encounter this a lot in trig. Okay, this is going to happen all the time. Okay, lines pass the horizontal line test. Y equals x, 1 over x passes the horizontal line test. A lot of functions do this automatically, or not automatically, but a lot of functions just do this without any restriction to the domain. But there's going to be times where you're going to have to do this. Okay. Another thing about inverse functions, symmetric. Right? Remember, we covered even and odd functions, but they are symmetric about the line y equals x. So if we go ahead and graph something like, here's my y equals x. Use this one. Right? Here's my y equals x. I know we do graph. I know there are a couple of homework assignments, at least in pre-calc, because they cover the same section here, just a little bit differently. I know there are some problems that make you draw them. I am not a big fan of those problems because I am terrible at doing it. So I'm unlikely to ask you guys like test questions for this. But here's what x squared looks like. I'm sorry, y equals square root, right? And then And then here is what y equals x squared looks like. Okay, so they are symmetric about this line. I'm like, well, there's nothing over here. Like, that's okay. Doesn't have to be. All right. Why did you draw it that way? Square roots, right? So here's 0. Here's 1. Right? If I take like y equals the square root of x and y equals x squared, right? You usually think x squared is bigger, right? But let's try something that's real easy. Let's try 0.5, okay? If I plug in a half here, what's a half squared? It's a half times a half. That's a quarter. That's here. And if I take the square root, right, of 0.5, I'm not going to take the square root of 0.5. I'm going to try, can I get 1 penny less? Can I take the square root of 49? And this is 0.7, which is going to be up here somewhere. So my y is equal to the square root of x here. It's bigger, right, than x, than y equals x squared, from 0 to 1. Okay, so roots are a little bit higher, a little bit taller than powers on the interval from 0 to 1. After that, everything changes. Okay, but it's always a useful thing to remember when you're in the middle of calc and you're trying to figure out, like, what's the area here? And you're like, I keep coming up with a negative number. And that's because you swapped them. You said x squared was bigger, and it isn't. So that's something to remember for a couple of years from now, or a couple of semesters. But yeah, so we're talking about inverse functions, and the properties are that they have to pass the horizontal line test, and they are symmetric about the line y equals x. Okay. The function composition. So if f has an inverse, right? So if f has an inverse, we're going to call it f inverse of x, right? So if f of x has an inverse, f of f inverse, that's what this means. Okay, inverse. Okay, if f has an inverse, f inverse of x, then f circle f inverse of x equal to x. So if we compose the two functions, right, we will get just the value x, and vice versa, because if you remember, composition is not, right, is not a commutative property, right? This is not something, you can't say g of f is equal to f of g. Okay, it's one of the few operations you know at this point where that does not work. Okay, so always try to remember that it's not going to go backwards or forwards. Okay, you have to check both of them if you want to make sure it's an inverse. So f of x is equal to, say, x squared, and g of x is equal to square root of x, and we'll go ahead and say on the domain x is greater than or equal to 0. So f circle g, right, of x. So we need the number squared, and what number would you like to square? We'd like to square the square root of x. It equals x. Hooray! And then go the other way around. What about g circle f? We have the square root, right, of what are we taking the square root of? Well, we're taking the square root of x squared, get x, okay, provided x is greater than or equal to 0. Otherwise, we're going to get absolute value of x, which is one of the reasons why we do this. But yes, that works as well. So we're doing pretty well. How do you find an inverse? Well, we're going to use this property of it being symmetric about y equals x, because we're going to, well, it's symmetric about y equals x, we can just swap them. So if I have, say I have I have y is equal to 3x minus 5, and we say, well, I'd like to know what the inverse is. Okay, so what we do to find this, right, is you write it in this format. Excuse me. 2, well, we're going to swap. Okay, there's a highly scientific term there for you. We're going to swap our x's and y's. Okay, they're just going to switch positions. So in this case, right, we're going to have x is equal to 3y minus 5, and then we're going to solve for y. Okay, so we have, right, x plus 5 is equal to 3y, and we're going to divide both sides by 3. So we're going to say this is x plus 5 over 3 is equal to y. I'm going to call that f inverse. Right? I didn't check to make sure that this was a past the horizontal line test, but it's a line, and except for the line y equals a constant, which is a horizontal line, they're going to pass the horizontal line test, right? 3y minus 5, 1, 2, 3, 4, 5 is our intercept. And then we have 3 quacks and 1 waddle. So it's going to look something like that. It will pass a horizontal line test. Okay. So this one, really, we could break this apart, right? We could say this is also equal to 1/3 x plus 5/3. Okay. We could also do that. So, we have 1/3 x plus 5/3. 5/3 is up here somewhere. It's close to 6/3, right? So it's close to 2, and it's going to do something like that. And again, it's going to be symmetric about my y equals x if I drew my coordinate system decent. Okay, maybe we could look at Desmos or something for that one. But we could test it too, right? We could say, well, what's f of f inverse? Well, f says we're going to multiply something, some number by 3, right? And then add 5 to it. Oh, wait a minute. This should be a, oh no, we're going to subtract 5 from it. That's it. Okay. Which number would you like to multiply by 3? Well, one where I said this one. So the 3's cancel. We get x plus 5 minus 5, and that equals x. So at least in this direction, it's an inverse. We also have to test it the other way. What's f inverse say to do? Well, f inverse says to take a number, add 5 to it, and then divide by 3. Which number would you like to add 5 to? Well, I'd like to add 5 to 3x minus 5. Okay. So if we go ahead and do this, right, these are going to cancel, right? Minus 5 plus 5, we get 3x over 3, which is equal to x. Okay, so I know I'm kind of cheesy because I picked a line. Lines tend to have really boring inverses because they're also lines, but it does get the point across with an example that's very accessible. All right, so yes, this relationship is a one-to-one function, so we're okay. And we could move on. We can check. All right, and then move to some different, hopefully some problems. See this one, not going to work because it doesn't. It crosses, the horizontal line test fails. It crosses more than once. Okay, I want to see what this one. Well, determine if the relation defines y as a one-to-one function of x. It's not a function, is it? Because it fails the vertical line test. So I don't like that because this function does not define y as a one-to-one function of x. I mean, it is one-to-one. I wonder what they're going to say. I'm going to say it does not because it's not a function. Oh, okay. Good. Okay. Sometimes you don't know exactly what they're going after, and this one they're testing both definitions for you. Okay. I think we'll just see if we can find one that's okay. Checking to see if they're inverses. We did that. We'll check one. When I find one that's like not a line, we'll do that one. Actually, that one had us graph it. Let's go ahead. Just take a look at this one. I think they're going to make us graph it. So we must show that. Oh, okay. They're going to be a little bit more formal about defining a one-to-one function. Okay, so they want the formal definition here. And what they're saying is that and I will never ask you the formal definition. Okay, so if A is greater than, or usually they do it this way, but as long as it's not equal, then f of a is not the same as f of b. Okay, that their functions are, the y values are different for different values of x's. That's all they're saying. Okay, so if f is not equal to b, then a is not equal to b. Okay, that's all they're trying to say with that one. No, what are they? If f is, oh, if f, so okay, well, let's try. I just thought it would be not equal to, right? Because that's not true. If f is greater than, why do they not like this? Are they saying it the other way? If f is equal to b, then I wonder if they're saying it this way. That is peculiar. So yeah, if f of a is equal to f of b, then a is equal to b. That's another way of saying it. Okay, assume that f of a is equal to f of b. What? This is a very peculiar way of doing this. Okay. But if that's true, then, right, if the only way that this could happen is a is equal to b. I was kind of hoping we were going to get, since a is equal to b, implies f of, okay, then f is not 1 to 1. Oh, f is 1 to, sorry, f is 1 to 1. Okay, because the only way that could happen is if they're the same. Okay. All right. That is, like I said, it's kind of an odd way of saying it, but there we go. 3x plus 4, that's equal to y. So we're going to say, well, let's swap them. Okay. Let us swap them. So if x is equal to 3y plus 4, and then we're going to solve for y. So x minus 4 is equal to 3y. Y is equal to x minus 4 all over 3. Okay. So there's our spot there. So y minus 4 over 3. X minus 4 rather. All right. And now we get to graph them. Okay, so let's see here. We have 3x. Okay. If 3x plus 4, this is our original function. Let's pick when x equals 0, y is equal to, right, 4. And I'm looking at this graph here. Let's pick what if x is equal to -2. So we have 3 times -2 plus 4. We get -6 plus 4 is equal to -2. So we need x is 0, y is 4. Excuse me. Excuse me. Okay. And then when x was -2, then we were at, no, we weren't. We were at -2. Dang it. There we go. There we go. 4, -2, 2. There we go. That looks like a slope of 3, right? 1, 2, 3, up. Right? And now we have to graph another line, which would be this one, x minus 4 over 3. Well, what happens if x is equal to 4? Well, we got 4 minus 4 over 3. That's 0, right? So when x equals 4, y equals 0. Right? And then let's pick any other number. Let's pick, I I don't want to pick 1 or 2 because I don't want to deal with the fraction. Well, why don't we pick x equals 0? No. Yeah, let's pick x equals 0. So we have 0. 0 minus 4 over 3 is negative 4/3. Okay, so we have 0 and negative 4/3. So what we're going to do here is we're going to plot that point. We're going to say 0, and we're going to say negative 4/3 here. Negative 4 over 3. Plot that point for me, please. This is here. All right, so we can go ahead and say we have here. And what was the other point for us? The point was 4, 0. All right, check. And it's okay for doing that. Okay, so when hopefully the problems you get stuck on, because I've seen a couple that don't give you the little coordinate axis to plot your points on, because the answers, you know, most of your convenient points are going to be easy and they're going to be integers. But you know, I'm not just, you know, it's possible to pick them so that they're not. So hopefully they have that, but if not, we'll kind of sort through. All right. Okay. Do we have one that's not linear? Okay. X squared plus 2, but x is less than 0. Excuse me. So in this case, we're going to say, well, f of x is equal to x squared plus 2, but we're going to go on the other side of this thing. Okay, so normally, right, it's a parabola with a vertical shift of 2, but it's only on this side. Oh, excuse me. All right. Oh, good. Okay. So graph this. Vertex is at 2, right? 0. When x is 0, y is 2. Curves opens up and place one other point. So let's see. So pick x equals like -1. -1 squared is 1. 1 plus 2 is 3. Okay, there's the 3 point. Okay, we're good. -1 squared. Did I plot this correctly? So x equals 0, y is equal to 2. Choose how it opens. Place one other point. Pick x equals, right, -1. -1 squared is 1. 1 plus 2. That should, I don't, oh, I know why. Okay. We have to snip. Okay. Pick a point we would like to cut this thing. 0, 2. All right. Plot the point there at the graph. And then we're going to erase that half of it. Okay. Didn't realize that they were going to make me do all of that. And now we'll recheck it. And now it's much happier. Where are we? There we go. Now it's happy. Okay, so that's an important thing to remember is you have to restrict the domain by snipping it with the little scissors. Okay, and the eraser. From this graph, is it a one-to-one function? Sure is. Passes the horizontal line test. We're good. It is. We're good. Okay, write the domain of f in interval notation. So my domain, -infinity up to 0. What's my range? I think that's going to come next. We have bracket because it actually hits. It hits 2 off to infinity. Okay. Domain is. I want to do that. hit negative infinity in there up to 0. Yeah, okay. And the range is going to be, 2 off to infinity. Excuse me. Wow. All right, now F inverse. Okay, so there's a couple of problems in this book that will make you do it this way. All right, so we have y is equal to x squared plus 2, right? And we're going to swap. So we have x is equal to y squared plus 2, and then we're going to solve for y. So we have x minus 2 is equal to y squared, and then y is equal to plus or minus, right, the square root of x minus 2. Which one do we pick? Well, the domain, here's my F version, okay, and here's F inverse. The domain is negative infinity up to 0. That's going to be the range of our inverse. Okay. The range of F, which was to infinity, is going to be the range, or the domain rather, of F inverse. Okay, so the domain swaps, the range swaps. Okay, so what I'm trying to decide, well, which one do I want? Which one of these is going to give me a range of negative infinity to 0, right? If I've got, here's my value, I could either choose this one or I could choose that one. I don't know which one to pick. Well, which range is going to be negative numbers? Down here. I'm picking negative. There's a couple of problems in this book will actually have you, it's like an ambiguous case, and you have to go through and do this in order to figure out what's going on. Okay, so don't be afraid, like, well, let me write this down and figure out where this has to map to, or where this has to map from, in order to get the right answer. Okay, so we are going to do here we go, negative square root. This was x minus 2. This is on, yep, x minus 2, because we were there. And that's how we're going to check this thing. Okay. Oh, they want us to graph it. Okay, well, that's great. We have here, right, x2 plot a second point. Okay, so when x is equal to 3, 3 minus 2 is 1. Square root of 1 is that. All right? So let's see if we can check. Was it happy? It looks like it was happy. Yeah, it was happy. And then write the domain of F inverse, right? So we did that on paper, but the domain of F inverse is going to be, right, 2 off to infinity. And then inverse, right, the range is going to be, excuse me, it's going to be negative infinity up to 0. All right, so that's, you know, they're going to have us do that a couple of times. Okay. All right. Let me go ahead and check. Actually, give me a moment. I'm going to pause this and I'll be right back. Zoom, very good. Okay. Let's see if we could find another interesting problem here. All right. All right, I don't think we need to do that one. We did one just like it. Okay, given the domain, right, and then the range, state the domain and range of F inverse, right? We could do that one. It's the same idea, right? They just switch position. So if we know that F is, right, we know that F is negative infinity to 0, and the range, let's do it this way. Set this up a little bit better. Okay, so here's my F, here's my domain, here's the range, is negative infinity to 3. So the domain of the inverse, right, this is F inverse over here, is negative infinity up to 3, and then this guy is negative infinity to 0. Okay. So I wonder if you guys have, their last problem is the same as the pre-calc last problem. I'm curious. Negative infinity up to 3. This one. So negative infinity up to 3. Are they going to make us check? They are. Oh, dear God. Okay, and then the range, right, is the domain here. So it's negative infinity up to 0, and we get to do that one. So we have negative infinity up to 0, checking, good. All right. So like I said, I wonder if they, I'd say only 18 problems, but at the same time, I realized like, oh my, there's 18 problems. No. Nope. They did not. Okay. One of the things that we're going to talk a lot about, okay, is if, right, here's my t-table for f, here's my x's, here's my y's. For f inverse, okay, we're going to use this in the next section. For f inverse, here's my x's and here's my y's. So the domain stuff swaps, right? Swaps over to the range stuff, or I should say the range here swaps to the domain. The domain swaps over to the range. They just swap positions. So if I make a little list of my points here, right? For f, we have the list of points. We have 2, 0, right? We have 1, negative 3, all right? And then we have, what is this? Negative 2, negative 5. For f inverse, we have the points, right? We have 0, 2, we have negative 3, 1, and we have negative 5, negative 2. All right, for my x, y pairs, they just switch order. Okay, so they're gonna graph the inverse. All right, so let's go ahead and plot some points. So we have 0, 2, right? We had negative 3, 1. So here's negative 3, 1. And then we had negative 5, negative 2. So negative 5, 1, 2. And then we'll go ahead and connect the dots. All right. See, they are a lot nicer than trying to do this by paper. We would have to like sit there and freehand it. It never worked out well for me. But we're going to use that technique in the next chapter, or the next section rather. So that's something that's going to happen soon. But that's kind of a neat way they have to do it. All right. Oh, this is a neat one. Let me show you this one first. All right. So we have y is equal to 1 over x. Then what we're going to do is we're going to swap them, right? We're going to see, can we find the inverse of 1 over x? We have x is equal to 1 over y, right? We swapped. So we have xy is equal to 1, and then y is equal to 1 over x. You can say, wait a minute, how is that possible? A function can be its own inverse. So if you have f of g, right, let's test it out. So this is 1 over something. What do you want to take 1 over? Well, 1 over x. That's just x, right? Because we do that thing, right? Invert and multiply, or 1 divided by 1 over x. Okay, it doesn't really matter how you do it, but you invert and multiply, you just get 1 times x, back to x again. Like which one was f, which one was g? I don't even know. So we checked it. But it's really neat to find functions that they're their own inverses. Back in the early days of the internet, okay, we used, when email was a new thing, okay, to keep people from reading over your shoulder, because that, in computer labs, if you have to deal with a public computer, this was a concern. You're writing a love letter, you don't want people, reading over your shoulder, mocking you for what you're doing. There was a command called rot13, which would rotate all of your letters 13 places up in position. Okay, I can't spell Julius, but that's called the Julius Caesar cipher. Is you just change the position of, instead of A is 1, like A is now 14, and you use the 14th position. Julius Caesar was the one that came up with that. I guess at the time it was ingenious cryptography. Okay, but today this is a little primitive, but we rotate all of the characters forward 13. But the really cool thing about this was if you pressed it again, you got back to the original message, right? Because you rotate them 13 and you rotate them 13 again, and you get the same message. You get the same, you wouldn't have to do anything. So the encryption code and the decryption code was exactly the same operation. This function was its own inverse, right? Encrypting and decrypting was exactly the same thing. So this will never happen. Like, well, it does for this. So that's the only real cool kind of thing I've ever come up with. But the inverse for this one is it's the same one, because this is like a 1 over x kind of a thing. So all I'm looking for is a 1 over x kind of a thing. It looks like this one, right? I want it to be around -1, 1. I like that one. Everything else is kind of a little bit offset. Okay. And I made a liar out of me. Let's pick this one. Okay. Not quite, but there we are. The reason I try not to ask those on test 2, because I'm just going to have to go back and make sure that everybody has the same one. I'll let you guys go ahead and solve that one. And okay, so the water level for one area of the Everglades National Park is originally 2.5 feet. While performing an experiment during a particularly dry winter, the water level is decreased by 0.016 feet per day. Okay, write a function representing the water level in days after the start of the experiment. Okay, so let's see, it's decreasing. Okay, so at 0, right, the level of the lake was equal to 2.5. Lake, I don't know if that's a lake, it's a pond, puddle maybe. And it's decreasing, so we're going to get a negative slope, negative 0.016 x. X equals days after experiment. And so this is y is equal to negative 0.16 x plus 2.5. That should be a plus. All right. And write an equation for L inverse. Okay. So we're going to swap. We're going to say x is equal to negative 0.01 x 0x 0.5. Okay. So we'll go ahead and subtract. So this is x minus 2.5 is equal to negative 0.016y. Divide both sides by 0.16. I wonder if it'll let me get away with that. Y equals. It doesn't really matter where you put the negative. It could be on the top or the bottom or in the middle. So I'm going to put it in the middle and hope for the best here. And then wonder if they're going to let me do that. Okay, so that's my L inverse. So let's see here. All right, L. Okay, so L is just equal to negative 0.0. Actually, we're going to do negative 0.016, because I know it yells at me if I don't put the leading 0 there, plus 2.5. Fortunately, everything's in feet. We're good. All right. right equation for all inverse. Okay, so that was going to be negative. We're going to say x minus 2.5. Oops. It's 2.5, right? Divided by 0.016. 0.016. Let's see. So let me get away with it. It did. Now, what is the meaning and what's going on here? Okay. So when we talked about the thing, right, the level was the water level in feet. So y is the water level in feet in the original function, and x is the number of days. So in the original function, right, the domain was the time, right, in days. The range was the water level. In the inverse function, right, they swap. So the domain, right, is the water level, and the range is the number of days after the experiment. Okay. When you have word problems like this, they can be awfully confusing, and I really do recommend, like, write out like what the domain is, right? It's the time, that's going to go to the range. Write out the range. That's the water level, it's going to go to your domain. So when they're asking about, right, they're saying, well, what's my water level? This 1.7, this is the puddle of the water is 1.7 feet deep. Okay, that's what they mean. So when I plug that in here, right, negative, we have 1.7 minus 2.5 divided by 0.016. Okay, that's what's going to happen here. Okay. So we have 1.7 minus 2.5 equals, and I know that there's a negative out front, so we can make this positive, divided by 0.016. I should have left the negative down below there. So that's going to be, and I know it's positive because I didn't deal with the negative. Okay, so that's 50. So the domain is when the water level is 1.7. The range is, that happened 50 days after we started the experiment. Okay, so sometimes it really helps to write that out so that you don't have to worry about, like, which one is which. So, 1.7 equals, inverse of 1.7 equals 50, means that a given water level of 1.7 feet, right, the time elapsed since the start of the experiment is 50 days. They are very generous to you. Okay, most of the time in a paper test, you say, C, evaluate this and interpret the meaning and context. You're on your own. Okay, so they're very generous. So I recommend, like, write this out just in case you guys don't have a just in case you don't have like a little guidance thing here. But that's how that works. Okay, so those are inverse functions. They didn't do my favorite one. They didn't. Okay, that's a pre-calc problem. That's not a oh, yes it is. Okay. But yeah, generally those are pre-calc problems. So I will restrict myself to the kinds of problems you did in your homework rather than go nuts and come up with my own. All right. And they didn't ask you the hardest question they did in pre-calc, so that's a good one too. Okay. So I'm going to go ahead and pause this or stop us here. Okay. Next time we're going to talk about exponential functions, and I know I've got to write a test for you guys and get that done. So I will fix that as well. So I'm going to go ahead and stop recording.